Okay. Come on. Oh, for heaven's sake. Being a pain. Thank you. There we go. All right, so let's look at this problem is labeled 25.1, which should be towards the back of your packet. The one that's labeled page 352, but it should be towards the back of your packet. Yes, this is going to be central limit theorem stuff. So I'll do a little bit of an introduction and talk about how we can do this idea. All right, so last time we talked about that if you had sums of independent types of distributions, what distributions did we get back? So one of the things we said that if we did a sum of Poissons, what kind of distribution do you get? A Poisson again. If you do a sum of exponentials, you get a gamma. If you do a sum of geometrics, you get a negative binomial. If you do a sum of normals, you get a normal, right? If you do sums of chi-squares, you get a chi-squared. If you do sums of normals, you get normals, right? What happens with the means and the variances when you do sums of independent normals?
They're added.
Yeah. Wonderful. Very quick. All right.
This is going to fight some.
All right. So, and in general, that's true for anything that's independent, right? If your x1, x2, out to xn are independent and identically distributed, oops. Then the mean, or the expected value of the sum of the x sub i's is going to be what? What can I do? It's just in general with expected value. How does the expected value behave with respect to sum? I can flip it, right? It breaks up over the sums. And what do we say about each of the x's? Okay, so if they're identically distributed, what can I say about the expected value for each? They have the same mean, right? I'll call it mu sub x for lack of just whatever the x is. And so all I'm doing is adding the expected the means up, so I'll just get n times the mean, right? Where that mu sub x is the common mean of all the x's. Right? We agree? Okay. Notice that that really has nothing to do, well, that has nothing to do with independence. All right? Expected value breaks up over sums no matter the distribution. The fact that they're identically distributed is what we replace the expected value of each with the same value, and we're just adding the same value together n times. So independence had nothing to do with this, correct? And the only place that we used identically distributed was that we had the same mean in all the places. Okay. Independence pops up for variance. Since they're independent, what happens when you do the sum of the variance, or the variance of the sum?
The covariance.
The covariances are all zero, so all I need to do with the variance then is sum them, right? This is where independence is important, right? If you were going to do this, if they weren't independent, you'd have to do 2 times the covariance of all the different pairs that you could possibly make. Okay? Which would suck, I agree. Okay? But there would be all of these extra 2 times the covariance of x sub I and x sub j whenever I is not equal to j. Not necessarily a fun thing to do. Okay? But again, they're identically distributed, so these all have a common variance. So we just end up with n times the common variance as well. So when they are independent and identically distributed, the distribution of the sum has a mean that is the how many ever copies of the mean we have, and a variance is how many ever copies of variance we have. Now, what the central limit theorem says, and it'll be one of the first things that we prove next semester for those of you going on to the second semester. Couple people. All right, so what the central limit theorem says is that if x1, x2, to xn are all independent and identically distributed, lots of words again, and if y is equal to the sum of the x sub i's, then the distribution of y is approximately normal if n is large enough. It approaches a normal distribution, but it's approximately normal with mu sub y equaling n times mu sub x, and the variance of y being n times the variance of x. I'm just using a common x for the common mean, and ooh, hey, that was fun. The common mean and the common variance for each of the x sub i's is approximately normal if n is, and I'm going to put this in quotes because I'm not going to worry too much about it. At least I'm not going to worry about too much about the theory behind it. But it's if n is large enough. And for our purposes, you need n about 30-ish. So if it's approximately normal, we know how to do probabilities that have to deal with normals, right? We've done all sorts of different things with probabilities with normals. So the idea is that if you've got things that are big enough, you can approximate the distribution with a normal distribution and just proceed like you did before with probabilities. Now, this central limit theorem is typically stated in terms of sums, but I can also do the central limit theorem with respect to the means, because if I look at the mean of y, or the mean of the x's, instead of just the x, if I look at the mean of those, what goes out in front here? If I look at the mean instead of just the sum, what goes out in front here? 1 over n, right? So what's that going to do to this mean here if there's a 1 over n in front? No, yeah, this is the mean of x, right? The n's will cancel. What'll happen here?
1 over n squared.
You'll get a 1 over n squared times an n, right? So you'll get a sigma squared to the variance over n in that case. So if y is x bar, then again, y is approximately normal with the mean of y equaling the mean of x and the variance of y equaling the variance of x over n. And again, this is if n is large enough. Grace.
Why do we have two different definitions for mu and y?
The first one, I'm defining my y as the sum of the x's. And in the second one, I'm defining my y as the mean of the x's. Would you rather me give it a different letter? They didn't answer my question. Would you rather me call this W? Does that make you happier?
Wait, so what's the first one? What's the second one? The second one's the mean.
The first one is just the sum of the x's.
Okay.
Just add them up. That's what it is. Okay. The second one is the mean. Add them up and divide by f. I just used y in both cases. I didn't mean to confuse with using the same letter twice. To make it better when I use a different letter? Okay, cool. All right, so let's go back up to the problem. Way back up here. All right, so don't worry about the answers anyway. We have x1 out to x36. We've got y1 out to y49. Is n large enough?
Yes.
Yes. Okay, cool. So that means that I can, if I'm doing something with the sum of the x's or the sums of the y's or the means, I can use approximately normal techniques. Okay? So my n's are big enough. All right, so they're independent random samples, which is also good. I need independence. They tell me the mean for the x's and the mean for the y's. They tell me standard deviations for x's and standard deviations for y's. So let's see if I can get this to move, because I know that I have a hard time getting it to move. I could ask Ashley to do it. She could probably do it faster than I could.
Here she is thinking, yeah.
Yeah, I could. Absolutely. All right. There we go. So this one was the approximate value of x bar and y bar. So what we need to do first, before I do anything else, is what do we know about the distributions of x bar and y bar? Since the n's big enough, approximately what type of distribution will they both have? Normal, right? What's going to be the mean of the x bar? It's the same as the mean for the x's, right? So it'll be 30.4?
Will it always be the same?
Yes, for when you're doing the mean of the means is always the same as the mean of the distribution, yes. Okay, what will be the variance of x bar?
144 divided by 36.
Okay. Where'd you get that, Alex?
12 squared.
Okay.
Given variance of x.
Good.
And divided by x.
Right. So they give you the standard deviation in this case and not the variance, right? So I got to square my 12 to get the variance. And then for the central limit theorem says that the variance of the mean is the variance of the population, the underlying distribution, divided by the number in your sample. So 144 divided by 36, which is a number, but it's 4. I'm guessing they made it a perfect square. Or 36 is 12 times 3, so the 12s cancel, you get 12 over 3, which is 4.
Whatever way you want, okay?
Yeah, I will. I'll do it however I want, Michael. Don't you forget it. All right. The mean of the mean of y.
32.1.
Okay, it's the same as the mean of y, right? The mean of sample means is the same as the mean of the distribution. How about the variance of the mean of y? Do the same kind of thing, right? So it's going to be 14 squared over 49.
Which is, Dr. Joe?
I don't know. What is it, Grace? Tell me. Hurry. Hurry. Hurry.
4.
Is it 4? I think it's probably 4. Because you get 7 squared times 2 squared over 7 squared.
What's the probability of 4?
This is 2 times 7, right? So I get 2 squared times 7 squared, and that's 7 squared. So you get 4. What?
I was going to see if you could do it like that.
I gotta give somebody else a chance, right? No, I don't.
No,
Okay, fine.
You are the professor.
you should.
Sometimes I wonder.
Fair enough.
Dr. Joe, you should just take our test at Theorem.
Why would I do that?
So we can get all these.
Let's see, he wouldn't do that.
It's okay, Dr.
Especially
Joe
for
and I
me.
have
Again, I already did it.
Right, Dr. Joe, we have a deal.
We have a deal? What deal?
Our theory deal
A theory deal that has nothing to do with probability? Yeah, we have a deal.
that we made.
that we had said that had nothing to do with probability?
That
Right.
everybody
Yeah.
agreed on.
We agreed that it had nothing to do with probability. Correct. I agree with you. All right. We good with how we found these values?
Yes.
Are we okay? All right.
The deal that
She kept trying to make deals with me how she could perform on her theory of interest final and get bumped up in probability. I mean, there was like 8 or 9 different scenarios, at least.
which I'm confident in myself that I can do.
All right. What are we assuming? What does the central limit theorem says that we can assume about x bar and y bar?
They're approximate.
They're approximately normal, right? This one wants the probability that x bar is greater than y bar. Right? So we want the probability that our x bar is greater than y bar. But if we do something that's normal, usually we have a number is bigger than, the variable is bigger than a number or less than a number, right? We're trying to find those. So what if I move these to the same side and have x bar minus y bar is greater than 0? Now I've got the difference of two variables independent of each other, right? We're assuming independence in this problem. And I'm doing their difference. So if I do the difference of normal variables, what kind of a variable am I going to get? Normal, right? Just like the sum of normals is normal, correct? The difference of normals is normal, right? How would I find the mean and the variance of x bar minus y bar? So just to write this down, x bar minus y bar is approximately normal. Let me call it W. What will the mean of W be?
(1/n).
Negative 2.1? How'd you get negative 2.1? Yeah, I don't think that's negative 2.1. I think it's 30. I agree with your 30.4 minus 32.1. I think you get negative 1.7, right? Yeah.
There we go. That's what he said.
I didn't hear his. Oh, I'm sorry.
It's a negative.
Negative 1.0.
Does that make the variance 0?
No. It doesn't. No. You're not remembering how to do the variance correctly when you break it up over a difference. What do you do with the coefficients in front of each number? You square them. So what are you going to do with the variance here in this case? I got to add them together, right? Because remember the variance of ax plus by is a squared variance of x plus b squared variance of y. In this case, you can think of the b as negative 1, right? So you're still going to add the variances together here. So our variance will be 8. Because the variance of each is 4, correct? Remember our variance of ax plus by? Right? But remember it's ax plus by. So a would be 1, b would be negative 1, so I have to square. Yes.
So if those had coefficients in front of them,
Yes.
the mean would just be that times it.
Yes. Yep.
Minus the other.
Right.
But we would have to do the a squared.
You still have to do the squaring, yes. Yeah, Megan.
So, since we found that the variance of x is 4, like either word is inside, then it's a 2, and since I don't understand why it's 4 plus 4.
I don't know what you mean by inside, sorry.
Because you're saying,
So, because we need the variance of x bar minus y bar, right?
yeah.
So that's the variance of x bar plus the variance of y bar, because I got to square this coefficient. This is 1 times x bar plus negative 1 times y bar.
Oh, and you're squaring.
I'm squaring those coefficients, so it's 1 squared and negative 1 squared. That's what gets squared.
Okay.
Does that make sense?
Yeah.
Okay. All right, so let's go back over here. So we want the probability, if I go down this way, I want the probability that W is greater than 0. I now have the mean of W. I now have the variance of W. So how do I convert this into a problem where I can look it up on the table? What do I need to do? I got a z-score, right? So z needs to be greater than 1.7 over...
2 squared.
Okay. I agree with you. All right, I got to subtract the mean. So it's 0 minus a minus 1.7 and divide by the standard deviation, which will be square root of 8. Do you have a decimal approximation for that? Okay. So I'll leave it as 0.60. So if I'm going to use the table, this will be 1 minus phi of 0.6, right? Because I got to flip it because the table will give me less than or equal to. We agree? Okay. So let's go get the table. And I need this number here. So 0.7 or 0.7257. Oops, that's not what I wanted to do. Where was I? Not far enough down, that's my problem. Still not far enough down. There we go. Now by the time I get down here, 0.7257. Okay.
I don't know. That's pretty difficult. That's pretty difficult. Dude, that's the guy that's done this his entire life to do that. That's pretty difficult.
That was hard. Yeah, Morgan.
So, how did you know to subtract the mean again with your y from your x?
It was the way the problem was set up. It asked for the probability that x bar was greater than y bar. I could have done it the other way. I could have subtracted the x over, then you would have been looking for the probability that y bar minus x bar was less than 0. I could have done it. I could have gone the other way.
Easier.
What's that?
It's exactly because then you wouldn't have had to do the 1 minus.
You wouldn't have to flip it, but
So
then your z-score still would have been negative then.
Ah, man.
So you're still going to have to flip something around.
Oh!
Should have taken a deeper breath. I could have gone longer.
So then, since we're subtracting problem, we subtract the mean.
Yes.
So like if it was x plus y.
You would have these. Yep.
So is that answer A or?
I must be. I don't know.
Well, I sure hope so, or we did something. There we go.
There we go.
I feel better now.
Okay.
Good Joe, I forgot.
You did forget last time.
I get to this time. Michael! That reminds me of Dwight. Anybody else?
All right.
I'm sorry.
Let's look at this one.
I thought it was close. Ashlyn's been hit.
Ashley got hit? That wasn't very nice. Ashley's been sick and you hit her? Seriously? What's wrong with you?
I'm a sick, twisted person.
We know.
You're going to have a hard time disagreeing with that.
Me put it on the same day walking to class.
He did? That wasn't very nice of it.
Wait, what happened?
You made fun of Ashley.
I did.
Oh.
Michael almost as mean as I am.
And that's saying something.
Really?
That's already happened.
Nice.
That would save me a lot of pain.
What?
So I'm gonna be okay with that.
All right, so tell me some things you know.
I know
N
that
equals
the
100.
exponential-
Okay, the n equals 100. I give you that.
Pretty sure the exponential is 1 over theta
That is what the PDF is. I agree with you.
So then
No.
it's 2.
Damn.
So the
Wrote it down.
new MCT would be 1 over 1 minus theta 2 to the alpha, right? It's the same.
I agree with you. That would be the new moment generating function. I agree with you. You don't need to know that either. This is good review stuff, though. You're exactly right.
Good about that.
So what kind? Well, then go ahead and tell me what type of distribution would the sum of the x of i's have? It would be gamma, right? Because it's the sum of exponentials, so it would be a gamma. Yeah, I agree. So that's good. That's good review stuff. Not germane to this problem, but good review stuff.
We know that the end is
Big enough for.
Yeah, it says it's big enough, it's approximately normal, right? Because our n is,
Oh, is that always a thing?
yeah, it's always a thing.
Oh, I thought it was, okay.
Yeah.
That's,
When you're doing the sum of independent and identically distributed variables, if n is big enough, the sum is also approximately normal.
oh, I like, no.
All right, so if w is this sum of the x of i's, what's your mean of the w is going to be? It's not 1/2 because we're not doing mean here. We're adding them. It'd be 50. Yeah, it's gonna be 100 times 1/2. We're not doing mean here, right?
Right.
We're doing the sum of them, so we don't have the 1 over n out in front at all. We're just adding them together. So it's just 100 copies of a distribution that has a mean of 1/2. So the mean overall will be 50.
And that's because we're doing a sum.
Because that's because we're doing a sum, right? Yep. All right, what about the variance?
I don't know. 5.
Ooh, why is it 25?
Because the variance of x is 25, because the variance of the exponential distribution is theta squared, 1/2 squared.
Yep. Good. That's exactly right. Your variance of your exponential distribution is theta squared. What's theta in this problem? 1/2. So each of the variances is 1/4, and we're going to add them again together, right? There's 100 copies of distributions that have, of independent distributions that have variance of 1/4. So that's where the 25 comes from.
Can you repeat that? Not the whole thing, I'm just not understanding. I understand that n is 100,
Okay. You understand why we got a fourth?
because 1/2 squared is 1/4.
Where does that come from? What kind of distribution are we talking about? And how do you find the variance of the exponential distribution?
That's a great review question.
I know, that's what I'm asking.
That's a big square.
It is that squared.
Which is why.
This is why it's 1/2, yeah.
Okay.
Yep. And then there's 100 copies of the same variable. So that's why we did 100 times it. Yeah? Okay. All right. We want the probability that the sum is bigger than 57, or the probability that W is greater than 57, not 50. So what do we need to do?
Z-score.
Yep, z-score, good.
You're killing the game, man.
Oops. So the probability that z will be greater than 7/5. Subtract 50, divide by 5.
Yes.
Right? So this is greater than, I got to flip it. And 7/5 is 1.4. And at this point, you should be able to finish it off by looking at the table, right? Yeah. Huh? Sure. Which one do I want?
1.4 right to the right.
That one?
Yeah.
9192?
0.08.
Why do I keep doing that? Thank you. There we go. Now I got it. 9192. He did a good estimation. I like it. That was good. He said about 0.08. It's perfect. It's exactly what he should be thinking.
He automatically used man probability.
Yes, I'm out of here.
On your probability exam. All right. This one okay?
Only. Dr. Joe, I don't mean to burst your bubble, but on the packet you gave us, you already gave us 28 like 2 weeks ago.
Okay. That's okay. So you got it twice. You get the light one on fire now.
You won't be able to make that sacrifice.
All right.
You do it pretty well. I don't know how to resurrect myself.
Is the mean 0.2? Is the mean of W?
Are you doing a sum or are you doing a mean of the sample? That's the difference between the two. Are you doing a total of things or are you trying to do a mean of things?
Total?
I think it's a total. So what do you think?
Well, I'm thinking it's not 0.2 now.
Good. I agree. It's not 0.2.
Doctor, what are the two things that we're combining?
What do you mean, what are the two things we're combining? I don't know what you mean.
I don't know.
I'm pretty sure we're combining 500 things here.
Combining two distributions. No?
Say that again? No, I didn't understand your question.
I feel like what we've been doing is combining two distributions and then finding the probability after we combine the two.
Okay, that's what we're kind of doing here, except we got 500 distributions we're combining instead of 2. Because we have 500 policies. So we're combining 500 things together. Apparently that bored you.
I'm just tired.
You didn't like that? You didn't like
My
that?
life is rough, let me tell
You didn't like that explanation?
I just don't understand it. But that's nothing new in this class, actually. I don't understand.
I think I got it.
Okay. Tell me.
I think the mean of W is 100.
Okay.
And I also think the variance of W is 100.
Okay.
So then we gotta do the z-score of 80 minus 100 over 10.
I agree. Yeah.
And then
Yeah.
you gotta do 1 minus that.
I agree with you. Yeah. Nice. All right. So we're doing a total here rather than a mean, right? We're trying to count number of claims. It says 80 or more claims, not an average of some number of claims, right? So I know that I'm doing the sum of these things, not a mean of these things. They're independent, they're identically distributed, and it tells you what the mean is of each one, right? So the mean of our W will be 0.2 times the 500. I know I wrote it backward from what I've been writing before, but you multiply the two numbers together, right? 500 times the 0.2. Same idea that we did in the last problem, isn't it? Now in this case, we have a Poisson distribution. We usually call them, what letter do we usually call the mean? Lambda, but also lambda is the same as what? The variance, right? They're equal for a Poisson distribution, right? So if the mean is 0.2, the variance of each is 0.2, and there's 100 of them. So the variance of W will also be the same exact computation. And then like Michael said, we want the probability that the sum of these things is greater than 80. So do 80 minus 100 over the square root of the variance. So z is greater than -2.
You want 1 minus p is z.
So I think this is just going to be phi of 2, isn't it?
Yeah.
By the time you rework everything around. Well, I have to do 1 minus for the greater than, and then I get a -2, and then I do 1 minus to take care of the negative because they end up canceling each other out.
That's dope. Now I feel bad. That you're gonna go down. Now on, it's gotta be like sideline pass.
Sideline that. Let's see if you can dive for it.
Yeah.
Okay.
So Michael didn't get it.
Is this one 9.9772? I think, if I remember correctly.
What? Because it entertains me and Dr. Joe likes it.
It does entertain me. I do. I agree.
Wait, Dr. Joe,
9.7. I was double checking to make sure I was remembered correctly. I'll go back. 9.772. That one okay?
Joe, when I did the,
well, your answer is what?
What did you get? Boy, 977 and change. It's not a 2.
I got 1.63.
Well, then that's not right. That's absolutely 100% not right. Can't be 1.63. It's a probability. That one I can say for certain. All right. How about this one? It's 160.
What's the? Is that just giving you the bounds for the uniform?
Yep. That's just, yeah. The 0 to 20,000 is the bounds for the uniform. Yep, that's right.
Is the mean 20,000 plus 1 over 2?
Why would it be plus 1? That's discrete uniform.
So this isn't, that's really what.
Yeah, this is not discrete uniform.
And
Can
can I
I
ask
we-
why?
Yeah, that's why do we know?
Because the loss amount could have change to it.
Okay, so I was thinking with the number of losses. Gotcha. So
These are loss amounts, so it's continuous uniform.
so it's big.
There you go. Good news is that you used the discrete uniform for that. It would have been that far off, right? Because 20,001 divided by 2 is about the same as 20,000 divided by 2.
Oh, I don't remember. I thought it was a minus b squared
Oh
over
wait, that's a
12.
different.
That'll work.
Is that what it is?
Because a minus b quantity squared is the same as b minus a quantity squared since you're squaring.
Is that
That's it.
what's 20,000 squared?
That's a big.
That's a big number.
I'm not doing any of this.
just doing 20,000 in your head?
No, I'm saying I'm just not doing it at all. It's just not.
Dr. Joe, why is that a big, I don't like that.
Oops.
As
I'm leaving it as like that.
We agree?
160.
We agree with those individual amounts?
Yes.
Okay. All right. We want the probability that the average reported loss is less than 9,000.
Oh, wait.
Oh,
that's bar. Bar.
So the W is our X bar in this case, right?
Dr. Joe, you don't need to do that.
I didn't do anything. So our use of X, or use of W is
1,000 or 10,000.
this is 10,000, right?
160. Oh no.
It's just 10,000, right?
Oh yeah, because those canceled.
Those cancel, right? Sigma squared of W is
Sigma over N.
the sigma squared over N, so it's 20,000 squared over 12 times 160.
Which is not a pretty number, so we're gonna leave it that way.
Because remember, when you take when we're doing the average, your variance gets divided by the N. So I'm dividing it by 160. So I'm taking the variance and dividing by 160, or multiplying by 1 over 160. Yeah? It's okay?
Yeah.
it's 5 to the 4th times 10 to the 3rd over 2.
Could you slow down? I'm not there yet.
Yeah.
So when we do the mean, are we not summing up the mean of that?
That's what the mean is, right?
I mean, it looks.
So if I ignore the 1 over N, I would get N times the mean, and then the N equals up front.
So your W is just, doesn't equal to the sum, like the past ones like ours.
I mean, it's equal to a sum of the X of I's, but there's a 1 over N.
I have like that.
I combine all of them.
Yeah, that's what I.
All right. So what do we want the probability of?
Z score of the two.
We want W to be 9,000, right?
Less.
Oh, less. My bad. My bad.
Joe, that's,
Oh my gosh.
what did we call it in numerical? That's a tick.
A tick mark.
So the probability that the Z score is less than 9,000 minus 1,000 over.
Square root of a very big number, which is negative 2.1.
Oh, great.
Is that what you said? Is
Whoa.
that not what you said?
That's what I said.
Oh.
That's not what she got.
I got that.
You got that?
Oh, we got two
I
people.
feel better.
I didn't do it, so.
Why not?
Why would I? You have the calculator.
I don't know what you're talking about. I don't see a calculator here.
You collectively have the calculators. Marshall's not double fisting, though.
It's not theory.
Ah. We good? Okay, so this is what?
1 minus C. Is that a capital P?
Yes.
That's a number too.
It is a
I
number.
always call row B and B row. I don't know why. It's because of the
Trophy.
Trophy. What?
Trophy, trophy, get it. Funny after.
Okay. The 0.9857.
So, Dr. Joe, what is it?
I'm sitting there trying to remember the 0.998. This, see, you made me forget it. 9857, is that what it was?
Yeah.
I don't know.
I don't either. It's what I'm asking.
Yes.
All right. Those problems okay?
Yes.
All right. So the whole point of the last couple of sections was being able to figure out what the heck's going on? No, what the mean and the variance are for distributions that are added together, or means of the identically independent, identically distributed random variables, right?
Yeah.
Okay. So we'll review a little bit for the final on Friday.
Will we have a pizza party too?
No.